So 2 weeks ago, we worked on calculating forces acting on objects. And last week, we started our introduction to bridges by predicting and building an initial bridge to see what we thought might work in terms of building a strong bridge. So now we're going to actually look at how to calculate the forces acting within a truss and how we can use that information to optimize our design. So some of the things you might have seen in the app you were using last week are these forces of compression and tension. And we've talked about these a little bit, but compression is that squeezing force acting on something. The tension force is that stretching force or something being pulled. So if you remember how our bridges acted, the top member would have been in compression, whereas the bottom one would have been in tension. It was stretching out. So a truss is composed of members joined together at endpoints called joints, and we often use welds or gusset plates at those locations. So for your example bridge that you did, that would have either been those connectors that we made with the 3D printer, or just where you put the glue at the edges. You may have noticed that many of the simple trusses that you looked at are composed of triangles, and that's because triangles are one of the strongest shapes. You can see kind of visually from this picture the difference between applying force to a rectangular body versus one that's got this support diagonally down the middle to form two triangles. When we press on the top joint, you can see it deforming or bending, whereas if we press on the bottom right-hand one, you see that that cross member, the diagonal member, is preventing it from going out of its shape. So we often see a lot of triangles in our trusses. You remember we talked about the different types of supports that we'll see on bridges, and one of those is the pin support. And if we remember, this supports the bridge in 2 dimensions. And what that means is that this pin is equivalent to having a force in both the Y and X direction acting on my object. So we want to consider that pin is the same as having kind of 2 forces acting on our object at that reaction or at that support location. Whereas the roller really just prevents motion in that one direction. So it's really in that direction that's perpendicular to whatever surface it's acting at. The way that we have it oriented right here, it's in one direction up and down. And both these example pictures you can see as well, they're kind of the up. It's preventing it from falling through the floor, falling off the support, but it's allowing it to kind of move horizontally as necessary and for various reasons like we talked about. But you could also sometimes see this acting in the other direction, like this example here, where it's acting horizontally, so it's preventing that motion in the horizontal direction. So think about something kind of leaning against a wall, might be more like a roller support. When we solve these truss problems, we make a few assumptions in order to simplify the calculations. And these assumptions are that all of the members are perfectly straight, the loads are always applied at joints, the joints are pinned and frictionless, the members have no weight in and of themselves, and members can only experience tension or compression forces. Now, this is really a simplified version, and in the real world, there's obviously many more forces acting on the object. The members do have weight associated with them, so bridge designers are really accounting for a lot of these different parameters. But for our purposes, we're going to consider these assumptions will apply to our problems. The first thing we want to look at is something called static determinacy. Something that's statically determinate means that we can mathematically solve it. So we want to look to see if the truss setup that we have is statically determinate before we try to solve it, because if it's not, then we won't come up with any solution. And we can do that very simply by this equation that says 2j is equal to m plus r, where j is the number of joints, m is the number of members, and r is the number of reactions. So that's those pin or roller reaction supports is r. Remember, the pin has 2 reactions and the roller has 1 reaction. Let's look at an example of calculating static determinacy. You see here that we have 5 members, 1, 2, 3, 4, 5. We have 4 joints, 1, 2, 3, 4. And then we have our support reactions, but notice that we have pins in both locations. So we have 2 reaction forces at each of these pin locations. And so when we put that into our equation, we have 2 times the number of joints, so 4 joints, and for members we have 5, and the reaction forces is 4. So we see that 8 does not equal 9, which means that this is not statically determinate. So we have to think about how could we make it statically determinate so that we can solve for it. And one of the most frequently used kind of simple solutions is that we change one of these support reactions to be a roller. So we very commonly see the setup where we have one pin and one roller, and when we do that, we only have one reaction force occurring on this side. And so then our problem, or our static determinacy calculation, would work out to 8 equals 8, and we would be able to solve that problem. So you see here, we've added in that roller. Now we only have one of those reaction forces acting on point C, and our problem works out, and it's now statically determinate. We could look at a more complex example. We have this Main Street Bridge in Brockport, New York. It has 19 joints, 35 members, and 3 reaction forces, that pin and roller like we talked about, which is a very common setup. And we see that that works out to be 2 times 19 equals 35 plus 3, and 38 equals 38. And it all works out to be statically determinate, which means that we'd be able to calculate all the forces acting within this bridge. Last week, we watched the video on statics principles, and that included several equations that we use for the equilibrium of a body. One of those was the sum of the moments. If we remember, moment is equal to force times distance. For something to be in that rotational equilibrium, the sum of the moments, the sum of all the rotation forces, has to be equal to 0. We also found that the sum of the forces in the x direction has to be equal to 0, so everything acting horizontally on the body. It's important that we'll pay attention to sign when we're looking at this, just like we did with our vectors. Remember, force is a vector. And generally, we're going to consider right to be positive and left to be negative. Similar to that equation is our force in the y direction, which also has to be equal to 0 for us to be in equilibrium. And again, we're going to use up as positive and down as negative. So to reiterate, our 3 equilibrium equations are the sum of the moments has to be equal to 0, the sum of the forces in the x direction has to be equal to 0, and the sum of the forces in the y direction have to be equal to 0 for our body to be in equilibrium. And so when we're solving these problems, all 3 of those conditions have to be true, and we can utilize all 3 of these relationships to solve for different portions of our problem. So let's look at an example truss problem, and our goal is going to be to find the forces acting on our object. So we're looking at the external forces acting on the object, acting on our truss, and later this week we're going to look into calculating those internal forces, what's happening within each member. So we see here that we have a pin on the left side and a roller on the right side, and if we remember, the pin is the same as having a force in the y direction and the x direction, and our roller is the same as having that force in the y direction. So we just start by placing those with forces or reaction forces at each of those locations. So those shapes kind of go away. And we'll label them, and it's important that we have kind of distinct naming conventions for all of these things as we start to work through the problem. So at A, we're going to call those reaction forces RAX and RAY. And at C, we're going to have RCY acting in the upward direction. So we're given dimensions. Between A and D is 3 feet, between D and C is 7 feet, and between B and D is 4 feet. And so we have angles acting at A and C, which are going to be important to know so that we can figure out the forces acting on this object. Now, for solving our external reaction forces problems, it's not going to be as important to know those angles, but once we get into the internal reaction forces, it will be important to know those angles. So we're going to start with it now because that's a good first step to start with, is kind of lining up all of our dimensions, all of our angles. Now, if we remember from our trigonometric functions, to find that missing angle, we're going to use our trig function, so SOHCAHTOA. Now we have the adjacent side, the 3 feet, and we have the opposite side, the 4 feet. So we can say that the tangent of angle 1 is equal to the opposite side, 4, over the adjacent side, 3. And so that's the same as the inverse tangent of 4 over 3. And we find that angle is equal to about 53 degrees. It's actually 53.1. Sometimes it's good to be precise. Then we can look at our angle 2 in the same way and find that the tangent of angle 2 is going to be equal to the adjacent side. It's that 4 again. Sorry, the opposite side, which is that 4, over the adjacent side, which is 7. And then we'll do the inverse tangent of 4 over 7 to find that angle 2, which we find to be 29.7 degrees. Okay, after that is where we get into finding our reaction forces. So let's keep all of our elements in the screen here. And we're going to be solving for RAX, RAY, and RCY using our 3 equilibrium equations. Sometimes it's useful to write those down to start, just so you remember all the steps that you need to go through. So we want to say that the sum of the forces in the x direction equals 0, the sum of the forces in the y direction is equal to 0, and the sum of the moments is equal to 0. So let's start with the sum of forces in the x direction. The sum of forces in the x direction, and we're going to look which forces are acting in the x direction. Well, on our body, we really only have RAX acting in the x direction. Well, all the forces in the x direction have to add up to be 0, which means that RAX has to be equal to 0. Now let's look at our sum of forces in the y direction. Forces we have acting in the y direction is our RAY. Remember, up is positive. We have our 500-pound applied force acting down, so that's going to be negative. And we have RCY acting upwards, which is going to be positive. And all 3 of those things added together has to be equal to 0. So we can simplify that to say that RAY plus RCY have to be equal to 500 pounds. Well, I think sometimes we're tempted to just say, okay, well, if both of those add up to 500, then let's just split the difference and we'll call each of them 250. Well, we can't really say that because we can see that they're at different locations in relation to where that force is. So between RAY and that 500 pounds is 3 feet, and between RCY and that 500 pounds is 7 feet. And so we can start to think about approximately which one do we think is going to have more force acting on it. Think about if you're standing on our plank, like when we did our deflection experiment, which side do you think is going to be experiencing more force? Which one's going to have to respond to more force? But we're going to do the math to try to figure that out. So then we use our last equilibrium equation, the sum of the moments, to figure out what's that distribution between the two. So the sum of the moments has to be equal to 0. Remember, moment is force times distance. And what I do is I pick one point, and I can pick any point, and I'm going to use that as kind of my rotation point and say, well, what would happen if I tried to rotate around this point using the forces that are acting on the object? So very frequently, we like to choose the point that has the most things occurring at it. And for this problem, that's at point A. So I'm going to look, okay, if I was going to rotate around point A, what's going to cause things to rotate around point A? Well, I have my 500 pounds acting down at D, which is going to cause it to rotate in this direction. And then if I was holding down on point A again, what else might cause it to rotate around? Point C, it's going to cause it to rotate around counterclockwise. Remember that counterclockwise and clockwise are important when we're talking about moment. Counterclockwise is positive, clockwise is negative. Okay, so if I'm going to calculate my moment acting around point A, I have my 500 pounds remember that's going to be negative, and moment is force times distance. Well, the distance between A and that 500 pounds is 3 feet. So 500 times 3, or negative 500 times 3, because it's going clockwise. RCY is my other force. I don't know what it is yet, so I'm just going to leave it in as a variable. And it's rotating around point A. It's 10 feet, the 3 plus the 7 feet from point A. And so I find that the sum of my moments about point A is equal to negative 500 times 3 plus RCY times 10. Well, if it has to be equal to 0, I can rearrange this to say that 500 times 3 has to be equal to RCY times 10. Well, I can simplify this by multiplying out my 500 times 3. I would get 1,500. And I have my 10 times RCY. I divide by 10, and I get that RCY has to be equal to 150 pounds. Okay, well, this kind of answers my question about which one of those reaction forces is going to be experiencing more force. RCY was at 150. So then all I want to do is figure out, well, what's going on at RAY? So I'm going to return to my force in the y direction equation, and I'm going to put in the 150 pounds that I found for RCY. So I'm going to say RAY plus 150 has to be equal to 500. So I subtract 150 from both sides, and I find that RAY has to be equal to 350 pounds. And so I found all the forces acting on my truss bridge now, my reaction forces, using my 3 equilibrium equations. The sum of forces in the x direction equals 0, the sum of forces in the y direction equals 0, and the sum of the moments is equal to 0. You're going to try out a couple of these problems on your own, and then we'll go over this in class a little bit more next time.